Hi, welcome to another episode of Rust. Why won't you let me do that? I really want to do that. Please let me do that. I promise it's safe. So when I write articles, I usually go way too in-depth into subjects that are very complicated, and sometimes I get asked, why don't you write about something simple for a change? And I hear you. Today we're going to do something real simple. We're going to read some lines from a text file and only keep around some of them for purposes. We're only going to keep the lines that start with a capital letter. Easy, right? Refreshing. Let's do it. All right, so we're going to need some lines. And here they are. We have 4 lines. They're all good lines. I typed them all in myself. So we're going to want to read this file into a single string. And this is us doing exactly that, using the read2string function that takes a path and returns a result that, if everything goes fine, contains a string. Here, in terms of error handling, we're unwrapping, which turns the result string into just a string. And if there was an error, it's just going to crash the program, which I will take the heat. So beyond this point, the entire contents of the file is in that binding called input of type string. Quick note, I did not type :string. This is just Rust Analyzer's way of telling me what the type of my binding is. And what we're doing next here is just printing it. So let's run this program and see what happens. Awesome, so we got the path right. The file does exist. We have permission to read it, and the reading went well. It is UTF-8, there's no encoding shenanigans going on, everything is fine. So now that we have the contents of the file in memory, what we want to do is consider each line individually so that we can filter out those that do not start with a capital letter. And one way to do that is to use the lines method that's defined on strings. There, so lines returns a lines, and the lines that it returns implements iterator, and the type of the item of the iterator that lines implements is string slice, &stir. And so what we're doing here is we're just iterating over every line of our input and printing it preceded by a dash. Awesome. Next thing we want to do, we probably should have some sort of way to determine whether or not the line begins with a capital letter. I'm pretty sure we can make a function for that, so let's make one. And there it is. So it is called starts with capital letter. It takes a string slice called s, and it returns a boolean. And this probably warrants some explanation. What we're doing here is we're trying to determine whether the thing on the left here matches the thing on the right. And the thing on the left is an option car. And the reason it's an option car is, what if we have an empty line? Well, if we have an empty line, it's going to have 0 characters. So this, which returns an iterator, is going to be empty. It's not going to yield any element at all. So next is going to return none, and so it's not going to match. So in our case, we also filter out empty lines, which we can check by just adding one of these in here. But if we do have some character, we also only want to match if this character is uppercase, as defined by the Unicode character database. So now that we have this function, we should probably actually use it. We can just call it, and just like that, we're only printing lines that begin with a capital letter, which is what we sort of kind of wanted to do. Of course, another way to do this is to filter this iterator and just pass this function as the filter, which we're going to do right now. And voila. Now the result of this expression here is an iterator that only contains the lines that start with a capital letter. And it does exactly the same thing as before. So now our program is feature complete. So we've done everything we set out to do, which is great. But let's go a little further. Let's say we did say we wanted to keep those lines around, and one way to keep those lines around is to put them in some sort of data structure, like maybe a vec. So let's make an empty vec and push each of those lines in there. There. So now we're making an empty vector here, And for every line out of this iterator, we're just pushing it into that vector. And finally, we are printing a debug representation of our vector. So if we run this, we should see, there it is, a vector that contains 2 lines. I am a good line, I will be selected. Of course, that's not the most idiomatic way of doing that. We could just use collect, because what collect does is exactly what we want. It takes an iterator and collects all the items into some data structure. All we have to do is say what data structure we want, because it is generic over its return type. What that means is if we call it like this, with no information on what the type of good lines should be, it doesn't know what the type should be, so it's an error. But if we add some hint, like maybe we use a turbofish, like so, or maybe we just specify the type of good lines a little, just the container, not the items, like so, which is actually my preference here, then everything just works, and it does the exact same thing as before. So this is good. We're doing good so far. Everything's fine. We have our good lines. They're in a vector. We are keeping them around just in case we need to do, well, that's not, okay. That's not, we're not keeping them around for too long, because right now, at the end of the main function on line 12, let's say, good lines just drops. And so all those lines that we've painstakingly filtered and collected into a vector just are gone. And so is input. Input also drops. Everything drops, in fact. So let's say we want to do something with those lines that takes a while. So maybe we don't want to block the main thread, because maybe the main thread is in charge of a graphical user interface, and we want to do that work in the background. So we just send the good lines to a thread. Let's try doing that. Well, here's us doing exactly that. We're reading the input here. We're considering each line individually, and we're filtering the lines, only keeping those that start with a capital letter here. Then we are handing good lines over to a thread, which is going to process them. Well, in that case, it's just sleeping for half a second and then printing something. But let's just pretend that it's doing actual work, shall we? And then we're also waiting for the thread to end. But that does not work. The compiler is not happy with that at all. But why doesn't it work? Rust, why won't you let me do this? This seems fine, right? Well, let's look at the error a little closer. So what it's trying to say here is that we are borrowing input for longer than it, okay, let's make a diagram. Here's the situation we have more or less. We have input, which is an owned type. So this one can live forever, but it's owned by the main thread. And then we have lines that borrows from input. This is the important part. Instead of allocating memory for each of the lines we want to keep, we're just referencing the original input string and just taking like little subsections of it, little slices of it. And then what we're doing is we are sending lines over to the worker thread. So if you just imagine that time is going downwards, we can just have a second point in time here where input is still owned by the main thread. It retains ownership of input, but lines is now owned by the worker thread, and it is still pointing to input. And the problem that we have here, the potential problem that Rust is trying to save us from, is what if the main thread suddenly stops and input is dropped, but lines somehow keeps existing because maybe the worker thread keeps running? Then lines is now pointing to what used to be input, but is now garbage memory. And so that's what it's trying to avoid. That's what it's trying to prevent. But another question is, do we really need input to be owned by the main thread? Couldn't we just send input along with it to the worker thread, so that instead of going from this situation to this one, we would just have this, and then even if the main thread ends, input remains alive, owned by the worker thread, right? Couldn't we just do that? Well, this is us trying to do that. input is still owned by the main thread originally. GoodLines is also owned by the main thread, and then we're trying to move both of them into that closure here so that they can be owned by the worker thread. But the compiler is not happy. It is not happy. So let's look at the error message a little closer. We see here that the error is still the same, but we also have a new error, cannot move out of input because it is borrowed. And that is true. We are borrowing it here. Remember, we don't allocate any special storage for the good lines. They are just slices of the input. And so they reference the input. And so in Rust parlance, they borrow from the input. And Rust is trying to tell us that we cannot move input because it is being borrowed. Again, it's kind of trying to avoid a bad situation. Let's look at it with a diagram again. So we have this situation again where the main thread owns input and lines is borrowing from it. And the next moment we are sending input over to the worker thread. Well, input has moved physically in memory from one place to another place, and now lines is pointing nowhere good. And that is what it's trying to prevent when it says you cannot move out of something that is being borrowed. And the reason why that's a problem in Rust is because moving a value in Rust is always trivial. It's always just memcopy. You're always able to take whatever isn't being borrowed right now and just dump it somewhere else in memory and it's fine. Apparently in C++, which I am no expert in, you can run some code whenever something's being moved, and so that maybe here would allow us to update the address that lines is pointing to, but this is Rust, and in Rust moves are trivial. They're only just memcopy, so we cannot do that here. But maybe we can get it working if we change the order of operations a little. What if we originally only have input in the main thread and not lines, just input, and then we send it over to the worker thread, just the input, which is owned. So it's fine. Nothing is borrowing from it right now, so we should be able to just move it there. And then in the worker thread, we actually separate each line, start filtering them, and remember which one we're starting with a capital letter. That should work, right? It's legal to move input from the main thread to the worker thread because it's not being borrowed. And at this point, the worker thread owns input, so it's legal for it to borrow it. Let's try that approach. There. I'm not seeing any red on the screen, and that's a good sign. I think this should actually work. And it does. Now, the only reason it works is because of the move keyword here. This is a load-bearing keyword. If we remove it, then instead of taking ownership of input, the closure that our thread is running is going to borrow from input. And the error in this case is going to be closure may outlive the current function, but it borrows input which is owned by the current function. Right. That makes sense. It's even telling us to add the move keyword, which is awesome. So as you can see, Rust is very concerned with the lifetime of things. But there is one thing that sort of bothers me. Actually, there's a couple things. First of all, on this line here, line 17, we're actually waiting for the thread to stop. That means that at this point, it's safe to drop input, right? Because the thread is done with it. Because we wait for the thread to finish. And when the worker thread is finished, it's done with input. So that should be safe, right? It feels like it should be safe, but it's not safe, and I don't understand why. So the reason here is pretty simple. The Rust standard library is being conservative. Because the thread can potentially live forever in a very positive version of the world where computers still exist in a century or so, it requires its argument, the closure, to have the static lifetime. And we can see that if we just hover over spawn, we can see that it wants an f of type f, which is a function that it's only going to be called once, pinky promise. It's going to take no arguments, and its output is going to be send and static, but also the function itself should be send and static. And that means that whatever the closure here captures from its environment has to have the static lifetime as well. And this is why it's okay to move input in there, but it's not okay to borrow from it, because a reference to input will not necessarily live for the static lifetime, because input will be dropped at the end of main. And if our thread outlives main, then that's a problem. But we've just said here that it doesn't outlive main. We wait for the thread to be done, and so it should be fine. So because the Rust standard library here is being a little conservative, we can just use another crate that will let us do exactly that. Crossbeam lets us create a scope in which we can spawn threads, and at the end of the scope, all the threads are joined, which means we wait for all the threads that are spawned inside the scope to be finished. And what that means is that the threads spawned from inside the scope can borrow from stack variables like input here. And this maps better to the mental model that I had of what we were trying to do, because we are waiting for the thread to be finished. So it should be able to borrow input, because main is not going to finish before the worker thread is finished. And if we run this, we can see that it actually works. So that was the first thing that was bothering me. The second thing that was bothering me, let's take a look at the diagrams again. This is what I don't understand. I understand that originally main owns input. String is an own type, everything is fine. And then it creates lines, a vector of string slices, which borrow from input. But then why are we not able to move both of these at the same time into the worker thread? That's the thing I don't understand. Because, and this is an important detail, moving the string itself is not going to move the data allocated for that string. We said before that input was a stack variable, but that's not entirely true. See, the part that's on the stack is only three things: a pointer to the actual data, the capacity, which is the amount of memory that we've allocated for that string, and the length, which is the part of the memory we've allocated that actually contains valid data. And the pointer actually points to some memory on the heap. And so what that means is that we can move that around anywhere, and it's still going to point to the same location on the heap. And if we're not convinced of that, we can actually try it out. In this version of the code, we are sending input into the worker thread. Input is being moved. And yet, if we run this, we can see that it's actually pointing to the same place in memory, the same area of the heap. So what I'm trying to say is, I don't see why this wouldn't work. I don't see why this shouldn't work, because we're moving both input and lines, which is borrowing from input, into a different thread. And so we don't care what happens to the main thread after this. As long as we hold on to input here in the worker thread, we can also hold on to lines. But because Rust prevents us from moving input in the first place, then we cannot do that. So now the question becomes, can we still do that? So let's take a look at this code. It's almost like what we had with threads, but instead we're trying to store both the input and the good lines into the same struct. And it's failing for the same reason. We cannot move input because it is being borrowed by good lines. Now, in the case of trying to store both the owned value and something that borrows from it in the same struct, there is one trick that will let us construct that. The trick is to first move input into the struct and then borrow from it, like so. And this actually does work. Here we have a self-referential struct. It contains an own string input and some string slices that borrow from another field. But this kind of value is very awkward to use. Here we're able to debug print it, but for example, we cannot even explicitly drop it. This doesn't work because the way the drop function works is it takes ownership of its argument and then does nothing with it. So its argument just falls out of scope and it's freed. But here we cannot move S because S is borrowing from itself. The message here says cannot move out of S because it is borrowed, and that is true. It is partially borrowed. Only s.input is being borrowed, but that still means we cannot move the whole struct. Even though we have everything we need for good lines to be valid inside of S, we would not be able to, for example, return it from some other function. Now we have a function called makeS that returns an S. The compiler is not happy. It's not happy for two reasons. First, we cannot return a value that's referencing local data. That is good. If we are borrowing from some local variable, then we cannot return that because we would be returning a reference to something that would no longer exist by the time we are done returning. And the second error we see is we cannot move out of S because it is borrowed, which is what we saw when we tried to drop it. But it feels wrong. Why are you not letting me do that, Rust? I know in my heart that this is fine. I know it is safe. Just let me do it. Well, this is a bad idea, and we're gonna regret that, but since we are very, very confident that what we're doing is actually fine, we can try to use unsafe. So the way that unsafe is going to help here is to decouple the lifetime of good lines from the lifetime of input. So instead of operating on input directly, what we're going to do is make a slice of the whole string. Like this, except this input slice that we're making here and then breaking down into lines and filtering and collecting into a vector is tied to the lifetime of input, which is not what we want because the compiler knows this borrows from this, so we cannot move input because it is being borrowed. Unsafe here can help us break down that link between those two lifetimes. There, now the input slice is unsafely built from a byte slice, which is unsafely made from a pointer and a length, which means that there's no longer any relationship between the lifetime of input and the lifetime of input slice. In fact, if we were to drop input, then input slice would point to garbage, which is very much forbidden in Rust and is the whole reason why we have to use unsafe here, because it lets us do things that violate the invariants. It lets us do things that are unsound. But to our credit, the code does compile now and it even runs. So who's to say if using unsafe in this situation is a bad idea? Well, in this particular example, it is mostly fine. But if we were to do some different things with S, which we're getting here from the makeS function, then things would quickly start to go south. For example, if we were to mess with the input field and replace it with another string, then things might start going wrong. Well, that's not right. It's not going wrong at all. It's still printing the... Why is it working? Why is it working? Wait a minute. Hang on. Hold up. Let's try doing that in a scope. Like so. Aha! Interestingly, only the first line is corrupted here, but the second line is fine. That's fun. That's in implementation detail of our memory allocator that's showing here. But here's the thing, as long as we didn't do that, as long as we didn't mem swap our way into chaos, things were fine. The unsafe was fine as long as we only used our S in a certain way. And so the challenge becomes, how do we make it safe to use S? Well, I have some ideas. If we move our S struct to a module, and we make the struct public, but not its fields, and we provide a way to construct a new instance of the struct in the form of a new associated function here, and also add a goodlines method so that we can actually get a reference to the good lines, then we can no longer do the swap. And that's how you make code safe, unless we forgot about something. And the nice thing is, we can even move S to a new function if we want. Here we build S in the main function, but then we pass ownership of it to new function, which we could not do previously when the compiler was aware that one of the fields was borrowing from the other field. So by putting the S struct inside a private module and making the fields private themselves, and only providing a careful set of methods to manipulate S, we made it safer. It is still possible that I forgot about something and you can still somehow mess things up with this version, but more importantly, now that we've added unsafe to our code, we have given up all the guarantees that the compiler would normally check for us. And so now anytime we add a method or change the behavior of the S struct in some way, we have to make sure that we enforce those invariants because the compiler is no longer looking out for us. And this is the bargain that we have entered by using unsafe. Now, if we add some other method that changes input, then all of goodlines becomes invalid. Here, for example, I've added a method named whoops, and what it does is just replaces input with another string. And if we call it, then the invariant is broken because now we have good lines that are referencing a string that no longer exists. And if we run it, we can see some garbage just as before, but we can also see a panic, and that's very funny because one of the slices start between 2 bytes that are part of a multi-byte sequence. And if we break up that sequence, then the result is no longer valid UTF-8, and Rust really wants all the strings, including string slices, to be valid UTF-8, so that's a panic. All right, well, that's all for this video. I hope you enjoyed the content. It was really fun to make. This is the part where I think I'm supposed to ask you to like, comment, and subscribe. If you want more of this style of content, please let me know on Twitter or otherwise. I'm still going to be writing articles. I'm not going to stop writing just because I'm making videos. I don't know how many videos I'm going to make. Let's see how this one does. Anyway, this was fun. Hope you had fun. See you next time. Thanks to all my patrons for supporting me all these months, writing these articles and now producing these videos. You all are awesome. For those who don't know, you can subscribe to my Patreon starting at $5 a month. $10 a month gets you name and credits, advents, access to some articles, and you can also create friend links so you can send those articles to your friends or colleagues. It's pretty neat. Anyway, thanks y'all for your support. Stay awesome and take care.